Mr. Chairman, ladies and gentlemen, it's 50 years now that modern science has started to investigate photo-induced water splitting for hydrogen and fuels. 50 years. I myself made in '68 a master thesis on zinc oxide when illuminated reacted with water, and I was participating quite a lot later in many initiatives. Now, even though many important groups worldwide participated, the fact is that today hydrogen from water is still 4 to 5 times more expensive than hydrogen from methane, from fossil fuel. Now, let us do the following. I will try to analyze the situation, and then I will try to suggest a change in strategy, which is quite dramatic. But before, I would like to say a few words about photosynthesis. You know that photosynthesis started 3.3 billion years ago, and it was so successful that there's a mechanism more or less stays the same during all the time. From genetic studies, we know that. Now, why is photosynthetic water splitting so important? It's important because sustainable materials and fuels were produced, and because today there was a lot of study about batteries. In fuels, you can store 20 times more energy per weight. And this is very important. Nature also gained a lot of experience with batteries. There are 70 species of fish that use batteries, but they don't use it for locomotion. They use it for communication, for hunting, for navigation and orientation, but in no case for locomotion, because it's more successful to use sustainable energy and fuel cells, yes, to power locomotion. Now, I would like to just show with one example how, I think it was too fast. Yes, how progress looks like. I was participating also in this effort here already quite, 2 decades ago. You know, photosynthetic water splitting works in such a way that you have a membrane with 2 excitation steps. Here, oxygen is evolved from water, and here hydrogen generated, normally NADPH, but if you have the right catalyst, you can energetically also produce hydrogen. Now, the practical systems, the technical system would look like that. You have 2 solar cells, one behind the other. You have a cathode and an anode, and here you have aqueous liquid. The efficiency was 18%. This is amazing, very much higher than nature can provide it. But nature optimizes many different parameters, so it's not aiming at maximum efficiency. No? Now, what's the difference now to biological systems? First, you don't have sustainable materials. Then the photovoltaic system is very different. The principle is very different, as I will explain in the following again. Then, for example, here for hydrogen evolution, platinum is used, and for oxygen evolution, ruthenium dioxide. These are the best catalytic materials which are technically known. But nature can work like platinum for hydrogen evolution with iron-only hydrogenase. It contains only iron and sulfur. It's as good as platinum, and the manganese complex is, with respect to the overpotential, 5 times better than the best material here, ruthenium dioxide. So we see already that nature is doing much better, and in the following we will investigate why this is the case. The manganese center for photosystem 2 is very well known and very important because it is succeeding in efficiently liberating oxygen from water. And this is a most critical step because you have to transfer 4 electrons. And when you take the first electron from water, you always form a radical. And this requires a lot of energy, so there's a lot of loss in energy. But nature succeeded in extracting all 4 electrons with very little overpotential. Yes, many synthetic manganese complexes have been produced, but until now there was not a real success. And I explain here and recall the simple reaction for water splitting. You extract 4 electrons. The first extracted requires 2.8 electron volt, and this is what happens with titanium dioxide. A lot of researchers try to use titanium dioxide for water splitting, but they never succeeded really in overcoming that problem. Yes. Now, I recall that many groups have tried to produce manganese cluster compounds. I just recall one review which investigated 171 manganese clusters, including 54 manganese 4 clusters. Like in photosynthesis, they were not successful. It was not possible to handle them in such a way that really efficient oxygen evolution happened, yes. The best material technically is the ruthenium dioxide, yes. Now, why is this happening in nature that you don't need a big overpotential? There was an important study a long time ago by Watanabe and collaborators. They very carefully studied the pH in the photosynthetic system and looked how much charge was turned over. They arrived at 12 milliamps per centimeter square, and they measured the overpotential needed for oxygen evolution. It was 60 millivolt. So 4 to 5 times lower than for the best noble metal catalyst we know. And this is something very amazing and unusual. Now, what is nature doing? We had a long history of involvement in this problem, and I would shortly explain you what's happening. In fact, what nature is doing, when the first electron is extracted, there's a feedback to the second, to the third, to the fourth electron. And when you calculate that, this is a self-organized reaction, and you find that the overpotential becomes very low and the mechanism very efficient. But in order to achieve that, you need a before and after. That means for feedback, you need a directed time. And this, I will explain later, is a big problem in science, the concept of time in these mechanisms. The time here is very important for feedback. Now, technically, one can calculate the efficiency for water splitting as a ratio of the enthalpies for the water system and the manganese complex. Then when you split it up, you get here an entropy term. What nature is doing, instead of producing entropy, is building up order. So TdS changes the sign, so the efficiency becomes big. But this, of course, has to be calculated differently because it's irreversible with thermodynamics, but the tendency is basically there. We studied this kind of self-organized electron transfer. You cannot use quantum mechanics because of the time problem also, as I will explain in the following. There's another important thing in nature. You know, nature uses photovoltaics. Photovoltaics means just that you have a membrane which, when illuminated, it generates a current. We are doing that by introducing an interface with an inbuilt potential gradient. Silicon solar cells work like that. Nature doesn't do that. Nature doesn't need a material which is stable for a long time to sustain such a potential, because ion transfer would be a big problem here. Nature has a possibility to rectify electron transfer. The electron is transferred and something happens with the environment which doesn't allow the electron to go back. And this practically is then the photovoltaic cell. It works like that when light arrives in the photosynthetic center, there is a charge separation, and then an interaction with a spin, nuclear spin, and so the spin of the electron changes, and this avoids that you have a reverse reaction. We have calculated the power that can come out, and the power is proportional to the rate constant and the chemical affinity. Both factors depend very much on directionality. The more irreversible the reactions, the bigger become these two, and the bigger the power. This formula applies also for the dye solar cell. It's a kinetical solar cell. Yes? So you realize that the time rectification is very important here, and this makes a big problem with developing this kind of technology. We are now, with our science, concentrated on quasi-equilibrium systems. Our electrochemistry, our physics is based on fundamental laws which can be inverted in time. Yes? Nature, however, works far from equilibrium, and there the energy becomes a dynamic variable, for example, and other factors also. Here you get self-organization, you get feedback processes, rectified electron transfer, and so on. And we cannot really approach well this field. Even, for example, we cannot derive the second law of thermodynamics from basic principles. We have to assume additional things. So this is a shame for physics, in fact, yes. But this is a problem that we are dealing with a natural science which likes to declare itself as time invertible. Now, to go more into depth with this kind of situation, our universe is basically a block universe where time is an illusion, and past, present, future is equally real because it depends on relative velocities. And you know that quantum physics involves a lot of paradoxes, for example, effect without cause, non-locality, and others. Elementary particles, for example, are also time neutral. The standard model, for example, cannot explain gravity, and there is no relation between quantum physics and cosmology, which is really established now in our physics. And with respect to processes far from equilibrium, neither the second law of thermodynamics can be derived, nor can our present physics say anything about an entropy law for irreversible thermodynamics where all these phenomena in nature are happening. So this is our big problem. What I will show, just with a few points, that when we introduce time orientation here, by allowing the energy to be active, because now the energy is just a number, a scalar, then we can really make a progress penetrating this area of irreversible thermodynamics. Time orientation would be needed very much in order to get a deeper scientific understanding, also to work with self-organization, with rectification, and with other phenomena far from equilibrium. But for that, I would like to recall early history. Heraclit in the 6th century before Christ. He observed that everything is changing, but speculated there must be something which is conserved. And this turned out to be energy. In the course of time, energy turned out to be what is reserved. But our energy, interestingly, has nothing to do anymore with change. It's just a number, a scalar quantity. Has lost any relation to change. And I think that this is a key problem, as I will immediately show you now with the next graph. The most important fundamental principle is the principle of least action. how a stone is rolling down from a hill. Yes? Well, the least action means the time integral over the energy involved has to become a minimum. Today, the energy has no interest. The energy is just the ability to work, but there is no interest. Time also is just a scale, has nothing to do with energy conversion. A clock needs energy, but then a periodic movement is used really, and the periods are just defined by parameters. So practically, this was a reason why for 3 centuries it was not understood what the principle of least action means, even though most laws in physics and chemistry were derived from that, yes. I think one would have to assume that the energy has a tendency. It must be a vector, and the time must be related to the energy, must be a consequence of energy conversion, which is not the case now, yes. Now, today, as already Einstein remarked, energy is like a beggar who is in fact a millionaire. He does nothing with the wealth. He has a potential to do it, but no interest. No, I think it would be necessary to make the energy dynamic, yes. The nature must be understood as fundamentally irreversible with a dynamic energy and a fundamentally driven time error in order to distinguish between a before and an after for feedback processes, which today you cannot do. Now, if you do that, this applies, of course, also for quantum mechanics. You know, today, particles and wave are considered equivalent. One mechanism works with particles, and the other with a wave, yes? I explained to you that, that there is a problem with quantum mechanics because, for example, the Marcus theory for electron transfer cannot be used to describe rectification feedback because it cannot describe polarization of the environment. So it's not possible to use quantum physics for going into the field of irreversible thermodynamics. Now, if you, however, define that energy has a tendency to decrease its presence per state, what you observe, for example, when you illuminate something, then the electron is first excited. At the end, you have many vibrations around, and the energy is distributed. When you assume that, you have to define the quantum process differently. You have to say the particle forms a wave plus entropy. But you need, for going back, information. So practically, you have to describe the quantum state as particle and wave, but with information to mediate in between. Now, this is very logic because in your cell phone, when you look at the system for digital analog interaction, you always need information to handle that. This is quite logic. Everywhere you need that from one system to the other. But when you define the quantum state that way, fundamentally irreversible, well, the particle has to provide energy in form of information to recover the wave back. And when you look at a particle spreading, then the particle is always remade via information. When you assume that, the quantum paradoxes don't appear anymore. This is something very important and surprising, in fact, but I believe that the nature is fundamentally irreversible. For example, when you look at an atom, the particle, an electron around a nucleus here, this particle, this electron, will also form a wave and information to recover the particle, the electron, from the wave. Now, also the energy for information is minimized here, and it will always only allow the assumption of certain orbits, because if the orbit would be chaotic, then the energy would be very high, in that case, much higher than the minimum. So you can explain quantization. You can also explain without assuming in these double-slit experiments that the particle assumes two positions in the different slits. You can assume that the particle converts into the wave and information, and this information sees the double slit, and you recover the information so that a particle going through one slit sees also the second. You don't need to assume, like in quantum physics now, that the particle has to go through both slits, so you have practically the presence in both cases. Also, concerning, for example, the constant light velocity, when you have a particle that always reestablishes itself from information, then it's the same as if you transmit information to an airplane. It's independent of velocity. So practically, you get also the constant, the always constant light velocity from this kind of consideration. So that basically, when you make the physics fundamentally irreversible, you can explain logically different phenomena, like, for example, the relation between quantum physics and cosmology, constant light velocity, quantization, and so on. Also, you can explain quantum correlation when a particle splits. You simply split also the information, and if the information cannot be split because for example, the spin has to be preserved, then you get this kind of quantum correlation. I come to the end and would like to say that when we abandon our view of nature as fundamentally reversible and go to a fundamentally irreversible world, we arrive at a logical universe, and this universe is also open for this effort to consider catalysis and via self-organization, kinetic stabilization of interfaces or rectification of electron transfer, because we have a before and after, so our time is some reality. When energy drives time, then time is a flow of action as a consequence of energy conversion, or the memory of information, practically, or the loss of information about the past. There is one interesting conclusion generally for society. One can, with a fundamentally irreversible world, also deduce that self-organized systems try to maximize energy conversion and energy turnover. So society will go on consuming more and more energy and endangering the environment. So I am at the end and would like to say that I claim that the time, neutral matter, and laws of physics, as well as the probabilistic time arrow, impede research towards irreversible thermodynamics. And if you assume practically an irreversible world, then I believe that you can handle a system accordingly. But this, of course, is a big effort. And to change a paradigm is something very difficult. For that reason, to start the discussion, I published a book which will come out in a few weeks. where I explain all these things in detail and hope that in the course of the time, some people will join me trying to investigate an irreversible world where everything changes like we see it in our environment. Thank you. Yeah.